Hello everyone, welcome to Engineering Explained channel. In this session, I am going to solve one of the thermodynamics problem. The problem is on that heat engine or refrigerator. It has the two parts. The first part is that a reversible heat engine operates between two reservoirs maintained at 500 Kelvin and 290 Kelvin temperatures. If the work output of the engine is 2000 Newton meter, evaluate the heat received and rejected by the engine. The second part of the problem is that if the above engine is operated as a refrigerator operating between the same two reservoirs, find the power input required for extracting heat from the reservoir of 290 Kelvin at the rate of 2400 kilojoule per hour. Here first we'll take the given data for the reversible heat engine, and if it is working as a refrigerator, we'll take separately given data. For the reversible heat engine, the high temperature reservoir temperature T1 equal to 500 Kelvin, low temperature reservoir which having the 290 Kelvin as T2. The work output of the engine is 2000 Newton meter, that is a 2000 Joule. What we have to find for this heat received and rejected, that is a Q1 equal to and Q2 equal to, we need to find out. If the engine is operating as the refrigerator between the same two temperatures, the given data are high temperature reservoir temperature T1 equal to 500 Kelvin, low temperature reservoir temperature T2 equal to 290 Kelvin. The heat extracting from the 290 Kelvin reservoir, that is a low temperature reservoir, is 2400 kilojoule per hour. That is a 2400 into 10 raised to 3 by 3600. That is equal to 666.67 joule per second. This is converted kilojoule per hour into joule per second. What we have to find for this refrigerator? Power input required for the refrigerator, WR, we need to find out. First we will take the reversible heat engine. In this reversible heat engine here, which is operating between the two temperatures, that is a T1 and T2. There is a high temperature reservoir. It receives the Q1 amount of heat. Part of it will convert into work output, and remaining waste heat it is rejecting to a low temperature T2 with the amount of Q2. And for this reversible heat engine, we have the thermal efficiency of engine as eta equal to 1 minus of T2 by T1. That eta equal to, we can write 1 minus of 290 by 500. The values T2 and T1 we can substitute, and here the eta we can write as 0.42. We can calculate. The thermal efficiency is also given by eta equal to We by Q1, that Q1 equal to We by eta. Then Q1 We by eta value can be substituted 2000 by 0.42. Therefore, the Q1 heat received, that is equal to Q1 equal to 4761.9 joule. The work output is given by WE is equal to Q1 minus Q2. Then Q2 can be written as WE Q1 minus of WE. Then that is a 4761.9 minus of 2000, that is equal to 2761.9 joule. It is a heat rejected Q2. Here we have determined the Q1 heat received and Q2 heat rejected. Moving to the next refrigerator, if the engine is operated as a refrigerator, it receives the heat from the low temperature reservoir at temperature T2 with an amount of Q2 with the help of WR amount of the heat input, and rejecting this transferring this Q1 amount of heat to the high temperature reservoir at temperature T1. For this, the heat extracting from the reservoir of 290 Kelvin, it is Q2 is given, as the Q2 is equal to 666.67 joule per second. We have COP of the refrigerator as COP equal to desired output and work input. The desired output, what it is required, the amount of heat what we are going to extract from the low temperature reservoir, and work input is the WR, and that also we can write Q2, and the WR work input will be difference between Q1 minus of Q2, that is a Q1 minus Q2 we can write. The COP is also given by in terms of the temperatures, that is a T2 by T1 minus T2. In terms of the temperatures, we can write the COP. All the temperatures we know, we can substitute 290 by 500 minus 290. That is COP for the refrigerator we can have as 1.38. The power input, how we can calculate, that is a WR equal to, from this equation we can have WR is equal to Q2 by COP. Then Q2 already we know 6.67, and COP we have calculated 1.38. By substituting these values, the work input required for the refrigerator we can have 48.3 joule per second. This is about this numerical. Thanks for watching. If you like, share, subscribe and comment, and further you can watch the other numericals also.